what happens is that basically bacteria are living inside us, right? And they all come from the mother. It's just the mother's mitochondria that's in you. So with the three parts where mitophagy happens, when your mitochondria is eaten up, is one, when the mitochondria divide, like bacteria, right? Some of them will have mutated DNA. And there are about 1 to 15 copies of the circular DNA in each mitochondria, and there's an average of 5 circular copies in there. But you don't know, the division of mitochondria is called stochastic, meaning it's random, right? So you don't know how many normal mitochondria you will receive and how many mutant mitochondria, and they will divide.
Greetings, everybody, from Washington, D.C. And we're back for, I guess this is the third time that we've had Dr. Ted in focus on the podcast. And today we're going to delve into one of your favorite topics.
Yes, mitochondria. And, being the third time here is, I think, an overexposure. I'm kidding.
Yeah, it's funny because I'm trying to think if we've done one in Washington, D.C. before, because we've done an episode with you in Manila. We've done an episode with you. I think the first one on metabolomics was remote.
Yes.
And so this is the first official one in person in Washington, D.C. in our sort of quasi research and development lab here.
Yes, it is. It is. And it's so much fun to have you here. And it's so much fun to work in a lab and, mix up little trochees and have a lot of fun doing that. And bioenergizing the mitochondria.
Perfect segue. So let's talk about my ninth grade biology class. I think in my ninth grade biology class, so equivalent age would have been, I don't know, what's that, 11, 12?
Probably.
11 or 12, right?
Yeah.
You graduated college at 11 or 12, I believe, right?
I graduated high school at 15.
Okay.
And college at 18.
Sure.
I entered med school at 18.
And I think for those listening right now, I might have got my ages mixed up because the average person probably didn't go to ninth grade until 15 years old. And maybe that's when they took biology for the first time. But let's go.
Yes, and I'm a biology major, by the way.
Yeah, so biology major. And I want to kind of point I have a bone to pick with my ninth grade biology teacher, who was also the swim team coach. But when I was in biology, we were taught, of course, that the mitochondria or mitochondrion was a part of the cell and that there was only one of them in the cell.
You're not alone there. I delivered a lecture to about 500 physicians, and it was over dinner, and I overheard, why? How many mitochondria are there in the cell? I thought there was only one. And he said, well, Dr. Ted said in his lecture, there's an average about 500 mitochondria in a cell. And really, but those with high metabolism, like the brain or the liver, would have about at least 1,000 in there because they need a lot of energy, right? And you could see that these organs, they need a lot of energy, but they have very poor energy reserves, right? So they have to keep on generating. So when you get older, actually, they are the first to go, the heart, the liver, the brain, and so on. And so even, the red blood cells, they say, oh, the red blood cells don't have any mitochondria. But actually, what's called the immature red blood cells called reticulocytes, they do, right? But many people, especially doctors, forget that hemoglobin actually comes from, the iron and in mitochondria. There is, there's a way by which the body actually eats up its own mitochondria. So it's called mitophagy. And that is to be really separated because you will hear very frequently.
So autophagy is a very sexy term.
Yes, it is.
Right? Like everybody in the world is like, oh my God, I'm fasting because I want to do autophagy.
Yes.
I want to autophagize. I want to be in autophagy all the time, right? And
well, euthanasia is forbidden,
Oh, well, if you live in the Netherlands, it's actually not. So anyway, mitophagy.
Yes, mitophagy is actually the cell eating up its own mitochondria. Autophagy is actually the cell committing suicide right? So that there are new cells that can actually be formed. Now, and there's a very straight up correlation between the mitochondria and, of course, autophagy, right? So autophagy is, of course, apoptosis, right? And then the cell is actually recycled. So this different mitophagy and autophagy are two different things, right? So there are three conditions where mitophagy happens. Of course, mitochondria are bacteria, right? They're bacteria inside the cell. And the number of cells in the body in a 75-kilogram male is about 3.72 times 10 to the 13
Who's
cells.
counting?
Yes, and that's in published literature. You can look it up, right? And we also have 10 to the 14 gut microbiota, and mitochondria is 10 to the 17. So you could see how this, I call them bacterial endosymbionts, meaning they're actually bacteria that live inside us. So
can we go into the endosymbiotic theory of evolution here? Because there's a key concept that we talk about a lot, the holobiont, right?
Yeah.
And I think this kind of goes into how you look at the mitochondria in general.
Yes. Well, if I'll finish the mitophagy part.
Sure.
So if you consider that the cell actually has an average of 500 mitochondria, and they divide like bacteria, right? They do fusion, fission, they move like bacteria, and so they have their own circular DNA and so on. So what happens is that basically bacteria living inside us, right? And they all come from the mother. So it's just the mother's mitochondria that's in you. So with the three parts where mitophagy happens, when your mitochondria is eaten up, is one, when the mitochondria divide like bacteria, right? Some of them will have mutated DNA. And there are about 1 to 15 copies of the circular DNA in each mitochondria, and there's an average of 5 circular copies in there. But you don't know, the division of mitochondria is called stochastic, meaning it's random, right? So you don't know how many normal mitochondria you will receive and how many mutant mitochondria, and they will divide. But the body senses if there is mutant mitochondria, because then it has a certain electrical potential that's very low, right? And when the body detects that, it actually marks it for, okay, I'm going to eat you up now, I'm going to regenerate you, right? So, and you could see there, there are marker proteins. You'd hear from very, very, erudite people, things like ubiquitin, and they shock you to death about it. But these are actually markers for death, right? Or recycling. And then the second condition where mitophagy occurs, of course, is when you are forming your red blood cell, right? You remember that the iron sulfur clusters, etc., of mitochondria are actually, enfolded into the hemoglobin itself. So the reticulocyte, or the immature red blood cell, will have to eat up its own mitochondria in order to produce your hemoglobin, right? And the third part is, of course, during fertilization, just in case the father's sperm mitochondrion enters the oocyte or the egg, the mother's oocyte will actually kill the mitochondrion of the father, right? Because it cannot have another electrical circuit in there, right? That's one half, right? It has to be a complete electrical circuit. So those are the three conditions of mitophagy. Now, for autophagy, that's a different situation altogether, right? Autophagy is a situation where inside the mitochondria, there is a molecule called cytochrome C. I know many of you there who are very familiar with the Krebs cycle would know what cytochrome C is, right? And together with what's called caspase 9, and those of you familiar with the CRISPR-Cas9 technology, that's a Cas9 9, that's caspase 9, right? These are the things that get out of the cell once a cytochrome C actually exits the cell in a pore, which they call the MPTP, mitochondrial, we just called it the permeability pore, right? And once it goes out there, it signals, okay, this cell is now marked for eating up. So let's call the macrophage, let's eat this up, and so that it could actually be recycled, right? So the cell can be recycled because the body is frugal that way, right? So that's autophagy. And we know that, for example, the things that we do, like intermittent fasting or fasting or ketogenic diets and all of those, they actually affect the autophagy, right? They affect, because they affect the number of new mitochondria that's produced. So mitochondrial biogenesis, right? So you have to distinguish between mitophagy and autophagy. Otherwise, because sometimes someone, more often than not, people talking to me about autophagy and actually oh, okay, that's really good for killing cancer cells, but, I don't really understand. Do you mean mitophagy, right? And I liken mitochondria to like kitchens, right? And so if you keep on feeding them, then they will produce energy for you, but it's a dirty kitchen, right? So if you fast, you're basically giving it rest, right? And it's a self-reproducing kitchen because they're bacteria, right? So a 12-hour fast is actually significant for you to produce new mitochondria. The old ones that have formed mutations, they're actually already recycled by the body via mitophagy. So that's the cycle. You were talking about the holobiont earlier. This just shows you that the cell is actually not a single organism. In fact, that's the Holobiont theory, or in the study of holobiontology, right? Where we are actually, each cell that we have is an aggregate of organisms that went into a symbiotic relationship with with other organisms and formed the eukaryotic cell that we now have. Remember that bacteria are prokaryotes, so you could see that the mitochondria actually has is double membraned, right? It has two membranes, and therefore, if you're taking like, oh, I want to take this or that from a mitochondria, well, one of the first things you ask is like, is it going to really to pass through double membranes, right? You have to ask that question, because there are many supplements out there that says, okay, this is good for your mitochondria, but will it pass the double membrane, right? So but the holobiont is very, very important, because if you take a look at the mitochondria, for example, it is showing how other organisms, like for example the Golgi bodies, or the endoplasmic reticulum, or other organelles within the cell, how they probably came to be. If you take a look at the mitochondria now, you could see that the circular DNA actually is just for the electron transport chain, right? They have the complete circuit to form the electron transport chain for energy production. But if you take a look at what about the membrane that surrounds them, and all the other proteins that need to be inside the mitochondria, those genes have actually been transferred to the nucleus, right? So the structural genes have been transferred to the nucleus. So you could see here how evolution does it, right? Well, okay, here you are now inside me as an endosymbiont, right? So okay, it's very expensive for me because I regenerate all the time, right? It's very expensive for me to carry all my genes and divide all my genes. Why don't you, supply me with the proteins that I need in order to build the next mitochondria? So you could see now the process. Like once upon a time, there was an aerobic organism, meaning it can process oxygen, right? That went into a relationship with an anaerobic organism, meaning an organism that does not process oxygen, and then and that anaerobic organism happened to reside inside, right? And now we call them organelle, but for me, I really treat them as separate bacteria, right? Because now and that's the holobiont concept, right? And it's very different from what we call a superorganism concept, Right? Superorganism is like you're actually a big organism made of the same type of cells, but it turns out that we're actually a single cell is actually made of different types of organisms, and that's why it's called the holobiont. We're an ecosystem of cells, and that's where the point of view that we take in health optimization medicine, for example, is that we don't take a look at the other humans as the ecosystem. We'll take a look at the human body itself as an ecosystem of cells that's all in a network and cooperating and competing with each other, for resources, for energy, etc. Now, the mitochondria is really very interesting because now you can do a yin and yang kind of thing, right? So you could see that there's a somatic cell, right, that produces energy by glycolysis, and it can function, it can produce energy with oxygen around. So that's the somatic cells in body. We'll just call it the nucleocytoplasm, right? The nucleocytoplasm, that's very structural, right? And if you take a look at that, most of our diseases are actually the way we studied in medical school. That's what I call the anatomical model, right? There's pathophysiology, your liver breaks down, your heart breaks down, your brain breaks down, etc. But then, so you could see that anaerobic organism is the one that we focus on in medical school. But then there's a bioenergetic model, which is now, okay, who's supplying energy to this? And then now you have the mitochondria, or the energetic model of the body, right?
So let's just recap this for people. So you have the anatomic model, which is what you're traditionally taught in medical school. And now we have the bioenergetic model, which is the model that basically looks at how the body is supplied with energy. Yeah.
Yes.
Okay. Now, if we're going to go down that particular vector of bioenergetic model, take us there. Take us on that dance.
Okay. So remember, each cell has an average about 500 mitochondria.
Not
right?
One, like my biology teacher told me,
or
right?
some physicians think. No, the whole bioenergetic body, and I love to actually explain this to students, is because the whole bioenergetic body opens to us how the body actually allocates energy. I think you have been in lectures where I actually say, the Department of Defense has the biggest budget in society. In the body, of course, the Department of Defense is your immune system, and it requires a lot of energy supply. So you could see that when you look at the body as an energy body, right, and with all these mitochondria that are communicating with each other, they are in communication with each other, right, and they're communicating with each other, responding to certain signals that are being given them. Hey, we need more energy here. Hey, this mitochondrion is producing too much reactive oxygen species. It's getting dirty. We need to shut it down. We kill it. Right? And so we have to produce new ones, etc. So you could see that the body automatically, by signaling molecules like hydrogen peroxide or nicotinamide adenine dinucleotide to NADP ratio, NADPH ratio, or the ratio of ATP to ADP and AMP. It uses this to sense your body's energy needs, your body's oxidation needs, etc. So in other words, like your anatomic body wouldn't be doing anything without the energy body. Okay, right?
So you're talking energy first in this case, right?
Yes.
Okay, so if we're now flipping from a bioenergetic to a bioenergetic model first, I mean, what are some of the key considerations there? Because I guess maybe take us through a few more things about what the mitochondria does and how that works.
Yes. There are two aspects to the mitochondria that I actually see, right? One is actually the one that actually produces diseases. So you can have, for example, mitochondrial diseases that are actually due to, in fact, defects in the mitochondrial DNA itself, in the circular DNA itself.
And we were talking about this. This is where like the functional threshold.
Yes, there are functional thresholds. Like, for example, if you have, they found out that the same mutation at a different percentage will have different manifestations. Like, for example, a 30% mutation, it may manifest as autism. At 70%, at 40% mutation, it may be diabetes. And at 70% mutation, it may come out as cancer. So you could see all of this. And these have been well studied, right? These have been well studied. You could see that usually at a threshold of about 70%, there's about chronic disease that manifests. I'm not talking about acute diseases. Acute diseases will be infections or trauma, right? But here, chronic degenerative diseases, especially, for example, in the brain, right? You could see that, for example, those familiar with the structure of the brain would be familiar with the basal ganglia, and that's where a lot of your dopamine neurons are actually are situated. So you could see that these have a very, very high metabolic rates, and they need a lot of mitochondria. So when you have a lot of mitochondria as you age, this mitochondria also decrease in population. They acquire a lot of mutations. In fact, there is even a beautiful diagram in one of the papers which shows that even aging, right? Aging, once you cross 40% threshold of mutation, is downhill from there. So but age will naturally do that to you, right? So for me, it's like, let's take care of our 10 to the 17 bacteria that's living inside us. It's just for me, it's like calling it an organelle for me makes it like as if I have owned it from the beginning. But calling it like bacteria, sort of like, oh, this is something that I have to take care of. Kind of like your gut bacteria. Gut bacteria, I call them.
But that implies that people actually take care of their bacteria.
Right. The gut bacteria, I call them exosymbionts, right? Because they live outside your cell. And for me, it's they should have the same status, right? As some mitochondria would be endosymbionts. They're inside your cell. They affect you. Mitochondria communicates with your nucleus, especially using hydrogen peroxide, and say, hey, we're all okay here. Or if spewing out too much hydrogen peroxide, it's like, hey, we're under stress here, right? So like any energy factory, they will throw out what they call reactive oxygen species, right? Any factory that's producing energy will produce toxic waste, and this happens to be the toxic waste, and that's how you come to the concept of antioxidants, right? So you have oxidation reactions going on all over the place, right? And then, like, for example, to produce energy from fats, that's beta oxidation. So, and so you could measure very, very quickly, right? You could measure, for example, metabolites that are produced inside the mitochondria. And at the same time, you could also measure what are the different reactive oxygen species markers that you could actually measure.
Before we get into measurement here, because I want to just sum up a couple of key points, or kind of get to a point of summary of why people should care about their mitochondria. Because we're going to get into measurement and correction here in a second, but
you know why they should care? Because if they don't, they're dead.
That's fundamentally a good point. But let's take, for example, the functional threshold. As you get older, and you're saying that at 40%, it sort of is downhill from there. The question that comes to mind is, can I go from 40 down to 30 rather than from 40 to 50? And so is there hope once you take a view that I want to optimize, I want to do something about this? Is there hope to improve the health of your mitochondria?
In fact, yes. One of the slides that I actually appreciated came from Aubrey de Grey, the biogerontologist, who, for some reason or other, we just solved an actual quirky math problem recently. But, he basically said that, these are not, essentially, we call this like chronic diseases, right? And actually, they are, when you look at them, and you don't take care of things, they actually become part of aging. So, but he has the senolytics approach. You're very
Yeah, he just
interventional.
he wants the
Yeah.
IP, pharmaceutical drug, that
Yeah,
kind of
yeah,
thing.
and
It's
it's a very good
sure,
framework, right?
sure.
But it's interventional,
Mm-hmm.
right? So I said, well, okay, someone's already doing the interventional. I hope he gets richer from the whole process. But there's a more tedious way of doing it, but doesn't require, the expensive senolytics and everything else, which is to take care of optimizing your hormones, nutrients, enzymes, etc., to be able to make sure that they function as if you were in your between 21 and 30 years old,
Mm-hmm.
right? That's because that's supposed to be the level for optimal health, right? Yeah, for
Okay,
all of
so
those.
I want to dangle that tease here for a second. We're going to
Yes,
come back to the correction components
yes, yes.
and sort of supplements, lifestyle things that
Mm.
we can do later.
Mm.
When it comes to detection of issues within the mitochondria, and
Mm.
let's say and we can take this from either a disease standpoint or even a health standpoint, right? You're
Mm.
looking at what do we have available to us right now in terms of testing, and that
Mm.
can include anything from like something that everybody has access
Mm.
to more advanced
Y- Yeah,
diagnostics.
you can, as I said, we didn't continue to start earlier. I'd like to finish it. It's like there are two parts. One is the actual mitochondrial disease, right? And that's a purview of illness medicine. And then within our purview in health optimization will be mitochondrial optimization. And in mitochondrial optimization, right now we could do metabolomics, right? We can take a look at the metabolites inside the mitochondria, take a look at the cofactors that are involved. And you know this very well. I repeat this like a mantra. You need B1, B2, B3, B5, lipoic acid, magnesium, in order to get the whole thing going. And then you have your toxic elements that actually, like mercury, arsenic, etc. That is fluoride that can actually disrupt the whole cycle, right? That's one is metabolome, but there's an index that has been there for a while. I think it was 2014 when it came out, and it's you could see it commercialized here and there, right? But it's called the Bioenergetic Health Index,
Mm.
and what it does is that it actually gives you your ATP reserve, like how much ATP is your cell producing, and how much can you improve it, right? So it's a very good test to do that. Initially, it was, I think, not very acceptable, but I actually was pushing for it. Is because it required a muscle biopsy,
Mm.
but now they can actually do it in your white blood cells because my white blood cells have mitochondria.
Mm.
So now that you could do it with white blood cells, then you could take a look now at you know what they do, a boomer, they poison each and every complex with a particular poison and see how it affects the electron transport chain, how many ATPs are actually getting suppressed in terms of production, and it comes with how many average your cell produces an average of so many ATPs, and this is how much you can improve your mitochondrial function
Mm-hmm.
in terms of increasing your ATP, right? And you could do that several ways, and I know you will touch on those later. But
So
for me, that's a more efficient index, and I've been preaching about it for what almost 10 years now. But
and there's a lab that I've worked with in the past in Germany
yeah,
that is doing the bioenergetic health index, and one of the things or one of the terms that you come across on the test results are perhaps vocabulary we should familiarize people with is this idea of coupling and uncoupling.
mm-hmm.
What exactly is that when it comes to the mitochondria?
Yeah, mitochondrial coupling is very simple. For every pyruvate molecule, or for let's just say for every food that you put in, the expected amount is exactly what you expect it to come out,
Mm-hmm.
right? So that's coupling. So it's one is to one for every say for every piece of food that you put in, this is the exactly the amount of energy. So 1 to 1 is equal, right? And 1 is to 1, you actually would find that beautifully in, for example, the endurance runners, right? Like Kenyans, for example, they win all of these endurance races, right? They have long limbs. They don't overheat when they run, right? And they run very gracefully and so on. And that's a particular, mitochondrial haplotype that does that. The haplotype is, your DNA, right? The combination of your mitochondrial DNA. And there are different haplotypes over the world because during the diaspora from Africa, and this is the theory, the diaspora from Africa, they call that haplotype L0, right? After Lucy zero. And then it went up and then down to, to the Bering Strait and then to Europe and then down to the Asia. So you could actually trace how the mitochondria has actually changed in haplotype based in its capacity to adapt to its environment, particularly cold. So those that are actually in warmer climates are actually more have a one-to-one coupling. But as you go to colder climates, it's not anymore. So you put one food in and you only get like probably zero point 0.7 or zero point 0.6 back. And why? Because the rest is actually expended as heat. Because you have to actually keep yourself warm in a cold climate. So you'll have problems, for example, for Olympic athletes, right? If they are sprinters and they train in cold climates, etc., and suddenly the sprint is in somewhere in the equator, they'll certainly lose, right? Because they will overheat right away. Certainly I had a case like that. But when you take a look at the mitochondrial haplotype, you say like you see that from the history, it's like all the wins will be in cold runs and all the losses will be in hot runs, right? In the hot environments, and that's not a function of a poor athlete, but rather a function of a mitochondria that's actually adapted to a colder climate, right? So you could see here the importance of for me, the mitochondria is actually the one that adapts you to your geographic area, right? And for those who actually migrate, you could see that the coupling of your mitochondria actually changes. Like for me, when I moved here from the tropics, right? I was a one-to-one coupled. Then suddenly here, I had to produce heat, right? So I would shiver and all of that. But then over
You
time,
must do really well in a cold bath.
yeah, and that's why sort of like Wim Hof. I actually like what you do, but I won't do it. I will plunge in a cold tropical river, but I'm not going to go into ice. But over time, you could have adaptations and changes. And mitochondria changes a little bit, but your haplotype actually, will try to adapt the best it can, right? By increasing your metabolism and so on. But you have to provide a lot more energy to do that. So and of course that will also mean that for anyone that you see, if you, for example, if you're a health optimization therapist, if you're a practitioner, right? Like I do, I am very particular about, especially for those high performance athletes. Or for those who are going to be, training in one particular altitude, and it's not only the EPO, etc. Really what's mainly affected is really your mitochondria, right? And then the race is going to be in the lowlands. You'll see, many will focus on the environment, but I would tend to focus more on what's happening to the mitochondria at the time, what particular stresses, because in the end, any competition, right, will be about how much energy you provide, or more importantly, modulate during the activity itself, right? And even in healing, it's very important. Why do you rest when you heal, right? There's a so-called triaging of the energy of the body, right? There's Bruce Ames, I think, is big in that. In that, if you, for example, are infected, right, the body will push its energy to fight the infection, and will put in the back burner repair of mutating DNA and trash collection and so on inside the body. So that's basically the body has to put in priority in its Department of Defense. So you could see that having an energetic model, and this goes back now to having not only an anatomic model of the body, but an energetic model, that the energy model actually has to do prioritizations on where it's going to send energy, right?
Mm-hmm.
And that also gives you pause on your activities during the day, right? When you have just eaten, for example, your postprandial. So what happens? Your body actually sends energy to digestion, right?
Mm.
And that's why many of us don't go running right after, right? So
I don't know many people who do.
so you could see that even now that you know this, it is even just by common sense, you could see, like, for example, in the morning, many people's minds are clearest, right? Because overnight the mitophagy has occurred, right? So there's new mitochondrial biogenesis has happened. There's new mitochondria providing energy. There's clarity, right? You're feeding on very little glucose because of the overnight fast. You have just 20 grams remaining probably that you can burn off with a brisk walk for
You're
40.
assuming a lot about people.
You could burn off with a brisk walk for about 40 minutes, and
Mm.
then you're shifted to a nutritionally ketotic state. And during those brisk walks, and it's really when you have that mental clarity. So, oh my God, I have so much energy. Well, do you think that mental energy is coming from? It's coming from your mitochondria.
Mm-hmm.
It's not coming from anything else, right? But like anything else, mitochondria require fuel, right? As I like to say, if you're doing basketball, for example, or sudden jerks and stops and really really powerful movements, you need a very dense and dirty fuel for that, and that's carbohydrates, right? Uh, but when you are going to go on, say, sit down in a chair and do long distance thinking, you're
Mm.
better off with a cleaner fuel, right?
The
What
endurance Excel thinker, right?
yeah. Well, what I mean by a clean fuel is that it produces less of the reactive oxygen species for the mitochondria that your body has to process. Of course, your body, of course, as I like to say, it has its own mechanisms to heal itself. I mean, it's older than our egos to think that we can control it, right? It has its own wisdom to know what's good for it. However, what's good for, and this is very very important for people to remember, what's good for the cell when it's deciding for itself is not necessarily good for the entire body, right? And for example, an example that I give is that if there is for example, a particular cell that's always getting irritated mechanically, right? And they say it's just a mechanical trauma, and the cell says, I don't want to. I want to survive. I don't want to persist in this mechanical trauma, etc. It will disengage itself from the network,
Mm.
right? It'll disengage itself from the network to control the network of the body, and then suddenly becomes a cancerous lesion. So
Mm.
you begin to have some skin cancer or something like that, right? And that's a cell deciding, well, my survival and reproduction, which is our primary evolutionary directive also, it goes down as a fractal, in the cell is survival and reproduction. And to us, we have survival and reproduction as an organism. But for us, it's like, that's a disease, man. But for the cell, if you put aside the cell, well, actually, I'm surviving and reproducing. So you could see it from the two different perspectives,
Yeah.
right? But your cell is actually doing what it thinks it should do for itself, right?
Mm-hmm.
And this is where the significance of the previous podcast that I had with Michael Levin, right? He has now developed something that keeps the cell in the network, in network control, so it cannot proliferate. So this is significance. That's why his studies are very exciting to me, right? And this is very, very, very much connected with how much of the mitochondrial energy is actually being put into that, right?
Mm.
In order to control something, you have to exert energy, right? It's like when you have a room that's in disarray. In order to put it back into order, you have to exert energy. And where's that energy going to come from? It's going to come from mitochondria. But remember, mitochondria comes from your mother. So if your mother is strong, energetic, and has if you do your DNA testing and you have longevity genes, etc., and you'll usually note that looking back, for example, looking at my mom, she rarely got sick. She had all of these markers of a very healthy mitochondria, right?
Mm.
And I have been very bad to it because traveling like hell, various different time zones, etc. But it's still very kind to me, despite the fact that I abuse it, right? Um, even if if I don't feed it for 18 hours, it just totally loves me.
Yeah.
So, people ask me all the time, what's the single best thing that you could do for your mitochondria, right? Give it a 12-hour fast. It's very easy. Stop eating at 8 p.m. You can start eating again at 8 a.m. But if you could prolong that by another 4 hours, and shift to a ketogenic mode, you have cleaner fuel burning, right? Until you get your first meal. So very simple stuff like those. You don't even have to supplement.
Yeah, interview done. So I guess, Dr. Sato, I want to take a sort of, not a pause, but a different angle here for a second, because there's, within our mitochondria, there's a lot of stuff that we can do to poison them, to release oxidative stress, etc. You mentioned one of them, jet lag, being my personal favorite one. But
yes,
also,
you're worse than I am. Before, my definition was being in the same time zone for at least 2 weeks, right? And you're in hell most of the time.
yeah, Sartre has a comment about that, but we'll leave that out for editing purposes. But when we talk about poisoning the mitochondria, and specifically there's some common drugs, supplements, those types of things that might poison different complexes. Can we go through those a little bit? I know they're all in published literature.
Yeah, they're on published literature. The most common one that I caution people about is actually, the new anti-aging drug called metformin. And I'd like people to actually get a longer view of this. If we were in the Paleolithic era and say metformin has been invented, it would never be an anti-aging drug, because you would not have any refined carbohydrates.
You don't like lilac, you mean?
So it works right now because we have so many refined carbohydrates in there. But metformin actually poisons complex 1 of the mitochondria. So even on my patients, because I do practice, right, in my patients with and metformin, I usually stop them on metformin at the 6th month of metformin, because they do experience weakness, right? Muscle weakness and decreased energy and so on. Yes, they actually lose weight, and but they're also weaker, right? In order to recover from that, I actually stop them from metformin and give them something else. There are natural products out there that are 1-to-1 equivalent with metformin. An example of it is berberine, right? Berberine is 1-to-1 equivalent with metformin. Another one that I actually use during this period, when I actually am actually preventing, or quote unquote, trying to mitigate the toxicity from metformin, is use alpha lipoic acid. It's also a hypoglycemic agent, right? So that's a very, very big one, because it has a direct bearing on the complex 1. And complex 1 is very, very important. It's the NAD, right, portion of the electron transport chain. And of course, you have seizure meds like valproic acid. There are certain antivirals that will affect it. And most of them actually affect the mitochondria by increasing the reactive oxygen species production. In other words, they stress out the mitochondria such that the mitochondria are throwing out a lot of trash that then the body has to recover from, right? And most of this trash would be something like, reactive oxygen species, hydrogen peroxide, peroxynitriles, and so on. And to clean those up, you also need energy to clean those up, and there's this whole craze, if you remember, on glutathione, right? Liposomal glutathione, etc.
Everybody loves it.
Yeah, and the reason for that is actually glutathione is actually in the detoxification chain of the cell, right? So in the liver, for example, the liver of the body is the detox part, the cell.
You mean the liver is not evil and must be punished?
No. One, if you could consider the cell as the body itself, right? And in fact, if you take a look at it, it has its own liver, and its own liver is is really a set of detoxifying enzymes that actually take out, all of these reactive oxygen species, and so on. And central to that is glutathione, right? Glutathione is made up of, it's called gamma glutamyl cystaneal glycine, right? And this and acetylcysteine is actually the rate limiting step. That's why you give, the cysteine is the rate limiting step. That's why you give, and acetylcysteine is usually enough to produce a jump of up to about 80% in glutathione if the enzymes are working properly, right, for the synthesis of glutathione. And remember, the glutathione has its own basically compartment inside the mitochondria itself too. It is also found in the cytosol, but it has a component in there. And in there, glutathione needs vitamin B2, it needs selenium, and all of that. But people are doing this, but really what it's doing, it really is just helping you detox, right? It's helping you detoxify all of this reactive oxygen species. It's not only one, it's just part of a chain. There's for those who are biochemically inclined, there's peroxyredoxins, there's thioredoxins. They're all in a chain that actually detoxify these things, kind of like the liver does with glucuronidation and all of those processes. There's also those processes occurring inside the cell. So you could see, you could just take a look at the human body and say, yeah, actually all of those actually occurring inside the cell. And this is actually, I like that. I'm able to stump students, like, so what's the equivalent of the brain, right, in the cell? And they usually say it's the nucleus. No, it's actually the cell membrane, right? Because it's the one responding in and out of the environment of the cell. But and if you go back again to the mitochondria, you see even the mitochondrion itself, its brain is its cell membrane, right? It has double membranes, right? It's double membranes. That's why for any supplement that you are taking, you ask yourself, hey, is this going to pass these double membranes, right? There's a popular weight loss drink. They're popular weight loss drinks that contain acetyl L-carnitine, right? And well, they work, but they really work at high doses, right? And if you really need them, because some people actually have normal, have optimal levels of acetyl L-carnitine, don't need them, right? But essentially, it's a shuttle of medium chain fats, right, into the cell so that it could burn the fats inside the cell. But what use is that if you're eating so much carbs anyway, right? So the first thing to do is probably to cut down your intake of refined carbohydrates in the first place, or increase your fiber intake. Because you basically use carbohydrates and fats for fuel. You rarely use proteins. Proteins are used for fuel only in terms of malnutrition, right?
Okay, so
well, obesity is also malnutrition, but I meant
well, in which case
I meant PCM, protein calorie malnutrition, like kwashiorkor or something like that.
All right, so we've gone through diagnostics and we've talked a little bit about how you can diagnose whether or not you have a mitochondrial issue, or said another way, how you can look to optimize your mitochondria through measurement, right? We've talked a little bit about different drugs you may want to avoid, not predispose yourself to poisoning mitochondria, aside from jet lag, for instance. And you've even kind of jumped down the wormhole a little bit with acetyl L-carnitine and some of these other things where we can start to look to optimize mitochondria. When we're talking about further along the lines of optimization, when you're taking a patient of yours through an optimization protocol, and let's say they do exhibit signs of mitochondrial dysfunction through oxidative stress or whatever, walk us a little bit through what some of that supplementation looks like, and maybe some of those lifestyle changes.
Yeah, in health optimization medicine, the big thing that I'm saying here is that lifestyle changes, we know that lifestyle modification is actually the most difficult part of the practice, but actually where you gain 60 to 80% of the improvement, right? So they have all this lifestyle medicine stuff. It's crap if you don't have anything to measure it with,
Yeah.
right? And you don't have any basis like, oh, we just do this, we just do this, adjust your lifestyle, and it becomes this. No, no, you have to proceed from what did you measure and how did it improve, right? So, for example, I can give you a couple of examples. The first example is that from, say, mercury poisoning, right? You don't know, this is subacute poisoning. It's not being detected as poisoning, but in your metabolomics testing, you see that the mercury is rising, and you know that mercury is going to stop, certain processes in your Krebs cycle, right? You can immediately put in alpha lipoic acid, selenium. It's, there are ways of dealing with it without actually doing the actual chelation with DMSA and all of these other chelating agents, right? And you can actually decrease those and watch your patient's energy improve. So what I had one patient that was this, and was just showing this signs, right? But when you take a look at the mercury is rising, and you could also see that when you put in like B vitamins to try to push it, right? It tries its best because B1, B2, B3, B5, lipoic acid, they all are part of that. So if you optimize those, there is salvaging that happens in the pathway that, okay, it may be getting poisoned right now, but at least your levels of all the cofactors, vitamins and minerals and cofactors are actually intact. Right, your magnesium levels, etc., they're actually intact. They actually help, but the real thing there is removing the offending toxin, right? So that's one. But in the more common case would be, for example, a person with chronic fatigue syndrome, right? Or what do you call this now? It's now called myalgic encephalitis, right?
Wow.
So it's no longer CFS, if I'm correct. So what you do there is when you take a look at these patients or clients for health optimization practitioners, they are just always fatigued. And if you take a look at their mitochondrial metabolites, and metabolites are called anaplerotic, right? Because they replenish themselves. And you could see that the levels are low. And you can actually see when that the B levels, usually they're the energy vitamins, right? They're also low, and at the same time, the anaplerotic agents are actually those that need to get replenished are not getting replenished. And that's where you should consider actually replenishing them with the actual metabolite in there. And when you do that, the functionality of the mitochondria improves. We don't know, what the final etiology of myalgic encephalitis is. Some people say, oh, it's mitochondria. Some people say it's this, it's that. But we don't care about the diagnosis. What we care about here is taking care of the cell. Okay, this is the best thing that we could do for the cell for its health, right? Whatever it is that's causing this, we take a look at that. What is it irritating the cell, and so on. So our focus shifts away from the organ into the actual cell,
So
and
you're
that's
going a couple of levels down,
down,
essentially.
right? And that's where the usual misunderstanding happens between health optimization, say, and illness medicine, right? Is that in illness medicine, it's like, what does it prevent? No, no, no. For us, it's what does it optimize, right? And these are two different processes, right? Because in medical school, we're actually taught to repair something before we even know you know, how can we do a Formula One engine, right? And we're not taught that. We're taught like, okay, it breaks down. Here's how you repair it, but we don't know how do I make this to optimal performance. We just assume that normal performance is optimal performance, and it's not, right? And the key here is that optimal performance is not the same for everyone, right? Because you'll have a different set of genetic predispositions, a different set of environments, a different set of even your beliefs will affect it. Like, hey, I don't want to eat that food. Like, for example, for me, um, people like my mother used to want to feed me nightshades, and I said, actually I get diarrhea when I eat nightshades, and she wouldn't believe me, right? And then finally, when
Want to look, mom?
so there are certain beliefs that are sort of pushed to you. So all of those predispositions actually affect. So that's why optimization of your health becomes very different for each person. Each person would have vegan beliefs, for example, or vegetarian beliefs, or things like those, and that will affect very much the optimization process. And that's why I said, you have to spring from the testing in order to recommend a lifestyle modification, because then you can come back objectively and say, look, we were able to move the needle here and here and here with this, and then the client or the patient says, oh, what else can I do? Right? What else can I do? And it
And it's a
snowballs.
feedback loop.
Yeah, it snowballs into a better and better health outlook. In fact, it's the only addiction that I advocate is
Success is addictive.
the
right?
the addiction to the feeling of wellness. Because when you get off the wagon, you know that very quickly, like, oh, I'm actually off kilter, I'm off balance, right? Let me get back on the horse, right? Like for men here, the way I scare them is like, you eat a scoop of ice cream, and 24 hours later your testosterone actually drops. But that's that's off mitochondria. Speaking of that, testosterone, because
I'd
it's
like to see how that jump was made.
yeah, no, as a fat soluble, it's a steroid hormone, right? And there's actually a hormone which we call a vitamin that is actually a steroid hormone. It's made from cholesterol, right? In fact, lanosterol is a base compound, and it's vitamin D. And it's like, oh, I'm so afraid of steroids. Like, dude, vitamin D is a steroid. But testosterone is a steroid.
Just test our biases or prejudice.
Right? Like, or anti-cortisol prejudice, right? But that's actually activated in the inner mitochondrial membrane, right? And what's interesting about the history of vitamin D, for example, is, since I'm vitamin D freak, right? The gene is like 750 million years old, and it's older than our species, and we retain it, so it must be useful for something. And as one of my dear friends said, we're yoked to the sun, right? And you could see that. And so at first, in the history of it, the nephrologists only had a purview of it because we thought it was for calcium regulation, and the activation was only found in the kidneys. And then they found out that alpha hydroxylase, which actually activated it, was found in all cells of the body. And that actually changed the attitude toward vitamin D. Until now, some of the old school doctors don't still know that D is activated all over the body. It activates around 2000. It activates around 2000 genes in your body, right? So that's that's, you have the inner mitochondrial membrane to thank for that. If not, it doesn't get activated at all, right? So
all right, so we've kind of run the gamut here on mitochondria and bioenergetics, and I think just before we close out, and maybe we'll dedicate the closing to my 9th grade biology teacher.
Okay.
If you were to kind of...
Oh, wait. Just one thing.
Okay.
I know that I've been pestered by some people about the urea cycle. And for those freaks out there, I just want to tell you guys, citrulline is inside the mitochondria. That's all I wanted to say.
Okay.
Please go ahead.
The urea cycle might be an entire another show. All right. So when we're coming to a closing now on the topic of bioenergetics or mitochondria, if people wanted to, let's say, learn more about the bioenergetics, perhaps how to implement this in practice, and maybe you want to send, let's say, my 9th grade biology teacher, if he's still alive, back to school to learn a bit more about the mitochondria, where do you send them?
Well, that's the reason why I actually was inspired to start the Home Hope Academy, right? homehope.org, where you can actually study clinical metabolomics, where you could actually measure the metabolites of mitochondria, and how to use supplementation to actually correct the imbalances. So we're detecting and correcting imbalances, not diagnosing and treating disease. And I'm very clear about that, right? And And then after taking the metabolomics courses, you could even just audit the bioenergetics course, and it's like bioenergetics or mitochondria,
Mm.
right? And there you'll see the all the things that we've discussed here and more, right, in a lot of detail, because I know that you guys are gonna shoot me if I started talking about VDAC and MPT pores and all of that stuff, and
Next time.
ANTs and all of that wonderful, beautiful stuff. We were talking off mic earlier about superoxide dismutases, manganese superoxide dismutase, copper zinc superoxide dismutase. You'll find it all there in the course, and why these minerals. Why are you supplementing with manganese? And yeah, that's from manganese superoxide dismutase. Why are where's your copper and zinc needed other from, in the mitochondria? It's actually used in the outer mitochondrial membrane, between the inner and outer mitochondrial membrane is your copper zinc superoxide dismutase, right? But manganese superoxide
I was
dismutase is
trying to
also
keep this
inside.
a little bit more commercial, but like,
but
we've
anyway,
gone there.
but anyway, that's my commercial. Is
Yeah.
that you will learn about that stuff.
Mm.
Like now, you will have a basis for why you're measuring manganese, why you're measuring
Yeah.
copper, why you're measuring zinc, right? And why you're looking at them intracellularly. Like serum magnesium will not do you any good, right? You have to take a look at intracellular magnesium, because that's what the body uses, right? The magnesium is in the serums only in transport. So you learn all about that stuff in the bioenergetics module. And there are other modules in there that are, of course, totally related. Evolutionary medicine is
Chronobiology.
chronobiology. There is gut immune system, of course, the 10 to the 14 organisms that we shouldn't ignore, right? There's epigenetics, which, by the way, it's actually, if you take a look at the body as two bodies, right? One is the somatic body or anatomic body, and one's the energetic body. Much of the communication between the two is done via epigenetics, right? These are control mechanisms that are not within the genes, but are outside of the genes, but they control how the genes work, right? And there's a whole a module on epigenetics there. There's also exposomics, which are the toxins that we take in. Little factoids like the fastest growing toxin in the toxin list are cosmetics, right? Things like that you learn in each of these modules. So there are 7 modules in total. It's metabolomics, bioenergetics, uh, gut immune system, exposomics, chronobiology, evolutionary medicine, and epigenetics. So, and those are all related. It was never taught to me in medical school. It's open actually to physicians and non-physician healthcare practitioners, right? So the home is health optimization medicine is for physicians, and hope is health optimization practice for non-physician healthcare practitioners. So come and check it out, because it's a love of labor and a labor of love. And I know Boomer has been the one leading the charge. And Dr. Ted, I want a more beautiful uh, face for home hope and so on. And
No,
thank you for
you're a very beautiful face.
and thank you for all of the students who have given us all the feedback, and who are many of them are already in active practice right now. It's very heartening for me to see that is finally someone is there are some people who are taking care of the basic cell, the fundamental cell, and what it needs, rather than going to the organ right away.
And depending on when somebody's listening to this, if you're in 2023 and not past October yet, you might want to come join us in Hollywood, Florida. I actually didn't realize there was a Hollywood, Florida until recently, for a little bit of a get-together, a home hope get-together, so to speak.
Yes.
So we'll include more about that in the show notes, but
yes, please come join us. It would be fun. Because aside from the formal lectures, it's a nice time for all the practitioners to be getting together, and just aside from swapping, we don't swap war stories. We swap success stories, optimizing stories, and of course, as always, they're exchanging points of view and different bits and pieces of important information that really keeps the community going. And in a very lively fashion. We don't fight with illness medicine like some other groups out there, we are actually there to actually support
Yeah.
the whole enterprise. In fact, we make illness medicine better.
There you go.
Right?
I think that's a great place to close. And shout out to my 9th grade biology teacher. Thank you for giving me so many questions to ask today. And thank you, Dr. Ted, for educating us on everything bioenergetics.
Thank you for interviewing me again.
Bye. That's a wrap for round 1 on bioenergetics with Dr. Ted Achacoso. And if you're like me, we paused this conversation and then I realized, holy shit, we could have covered so much more here. And we certainly will dig into this topic a little bit more. If you enjoyed this podcast, or if you're listening to it on Spotify or Apple Podcasts, please leave a 5-star review and a comment. Everything really, really helps. And if you're listening to this or watching this on YouTube, please like and subscribe. We, of course, want to hear from everybody, so please leave a comment as well. Thank you for tuning in to the Smarter Not Harder podcast, your home to 1 cent solutions to life's $64,000 questions. Have a great day.